All right, we need to get started. Y'all pick those up quick. All right, I'm going to give you all like another 30 seconds to get your stuff. That was yours? Okay, make sure you give that back to me at the end. You mind shutting the door? Thank you. Can you turn the handle and see if it's unlocked? It is? Okay. Okay, I've also handed to you your newest and last mini exam. By the end of today, you should be able to do the first 4, possibly the first 5, depending on how far I get. All right? And that is due on May 2nd. I have the wrong date up there. That date has already come and gone. So, all right, so let's get started. Y'all ready? We're getting to the final stretch here, right? We only have, 3 weeks, 6 class meetings, and then a final exam after that. So we're going to start 13.3 today. I have posted the homework videos, the solutions, to 13.2 and 13.3. I did 13.3 this morning, so they should all be there. To get this going, I thought I would remind you about something you learned in Cal 1 at the end, maybe Cal 2 for sure, and that was the fundamental theorem of calculus. We've been using this for a while, haven't we? So if we had a function of a single variable and we wanted to know the area below the function down to the x-axis, all it turned out to be is us being able to find the antiderivative of that, right? If we could find the antiderivative of that, then all we'd have to do is plug in the 2 endpoints. Plug in B, plug in A, and we're in business. So another way I could have written this is to actually write the connection, the relationship between capital F and little f. Remember that capital F is the antiderivative of little f, right? Or in other words, little f is the derivative of capital F, right? That's equivalent to say it that way. Now, today is about what's called the fundamental theorem of line integrals. And I told you before that a line integral is just adapting what we've done into curves that don't necessarily have to be straight lines. Because here, our interval from A to B, that straight line segment, is really the C that we're integrating over that we've been doing, right? Okay, so you could look at this as a generalization of the fundamental theorem of calculus. All right. Make this a little bigger. So here it is. If C is a smooth curve, all right, smooth meaning we're not going to have any weird, jaggedy edges on it. If C is a smooth curve, it's given to us by the vector function r of t. We're given a time interval from A to B. And if f is differentiable, okay, so look, this f here is a scalar function, right? If that f is differentiable, a differentiable function of 2 or 3 variables, such that, what? The gradient of that scalar function is continuous on C. That just means that when we take the gradient, it's well behaved. Okay? When we take the gradient, we look at each of the component functions, each one of those are nice continuous functions. If that's true, then check this out. The line integral of the gradient of f. Now that's a vector, right? And I'll remind you, the gradient of the scalar function f is going to be the partial of f with respect to x, then partial of f with respect to y, or it could be 3-dimensional, like that, right? It's one or the other, depending on how many variables we're working with. So if we take the gradient of the scalar function, which is a vector, which means this is a vector field, right? And we do dot dr, then it's just equal to, look, the scalar function evaluated at r of b minus the scalar function evaluated at r of a. So what the hell does that mean? We have some curve, right? This might be in two-dimensional or three-dimensional space. R of t draws that curve, right? Then if I asked us to find the work done, we did this last class, work was defined to be the line integral over the curve C of the vector field dot dr. Remember that from last class? This fundamental theorem of line integral says if this vector field, if it is the gradient of a function, little f, right? If it is, then all you have to do is evaluate the little f, the scalar function, at the two endpoints of your curve. And that would be the work done. But there's a huge requirement here. We must have that our vector field f, right, is the gradient of some scalar function. Okay? This theorem also says in some way that the line integral of a conservative vector field, right, is simply the difference of the value of the function of little f at the endpoints. Okay. What does that mean? Do y'all remember what it meant for a vector field to be conservative?
I was just reading it. You have to be able to go from a gradient.
Okay, so yeah, if we go back, let me see if I have 13.2 open here. I think I do. I think it's in here. Might be in 13.1 now that I think about it. Who's going to find it? Vector fields. Conservative vector fields. A vector field f is called conservative if basically it's the gradient of some little f. So that's what that theorem is saying, is that you can just evaluate the scalar function at the endpoints as long as that field was conservative. So isn't it going to be very important for us to determine whether or not a vector field is conservative? Because if it is, we can use this. So naturally, the question becomes, well, how can you tell? Right? How can you tell if a vector field that you're given is conservative? Well, let's just work one out first, okay? Let's say we're given the scalar function, f of x, y is x squared plus y squared. C is given by the vector curve there. Find this, right? Well, is this going to follow the theorem of fundamental theorem of line integrals? Yes or no? Yes, because they're asking us to find the line integral of the gradient of f, right? And we know that if this is the gradient of little f, then it's conservative because it came from a little f. So I know that the fundamental theorem of line integrals holds here. So all I have to do is evaluate f at the two endpoints, right, of the curve. Understand? Now, what is r of b? Well, what's b? What's a, what's b here? A is 0, and b is pi, right? So let's just real quick over here figure out what's r of a. Well, that's r of 0. And that means where am I on the curve when I plug in 0? So plug 0 into the curve function for t, and you get what? 0, 0, right? So I get the vector 0, 0. Understand? Let's figure out what r of b is. That's r of pi, which would give me what? See, pi, what's sine of pi? 0, so this is 0, and then pi times cosine of pi. Cosine of pi is negative 1, so we get negative pi. So according to the fundamental theorem of line integrals, this is just equal to f evaluated somewhere and f evaluated somewhere, right? This is where we have some tricky notation, which I alluded to a couple of classes ago. What does it mean to evaluate a scalar function on a vector, or at a vector, at a point that's a vector? Well, we're going to plug in 0, 0 here, and we're going to plug in, oh, wait, got it backwards, sorry. This one is 0, negative pi. And this one is the vector 0, 0. So all we mean, bless you, is you take your scalar function, you replace x with 0, you replace y with negative pi. So what would you get here for this first one? Pi squared. And then over here, 0. 0 squared plus 0 squared. So you get 0. So your answer is pi squared. Understand? Are you sure you understand? Okay, there's no magic to this. Now let me show you, briefly how you could make this, how you could have made this problem a lot harder. And that's by not understanding that you can use the fundamental theorem of line integrals. So what you do is you say, okay, well I know how to do this. And you say, I'm going to have to figure out what the gradient of f is, right? So you go, all right, I'm going to go here. I'm going to go from 0 to pi. Gradient of f is what, 2x, 2y. That's a gradient of f. Then you're going to dot that. What's dr? The derivative of your curve, right? Okay, which is, product rule here. So sine t plus t cosine t, and then derivative of that one, which would give you cosine t minus t sine t, right, dt. And then you would have to replace your x's with what? What would I replace my x with? With the x component of the curve. So this would become 0 to pi, 2 times t sine t, comma, 2 times y, so 2 times t cosine t, and then sine t plus t cosine t minus t sine t dt. Understand? Then you would dot them, and then you'd start integrating. And about 15 minutes later, well, we're all outside throwing the football around, you're still doing this, right? And we've already got pi squared. So you could do it this way, maybe. I don't want to do that integration. But that's a major time killer right there, right? Okay. Oh, what the hell was that? All right, we have a theorem that has to do with what's called path independence. All right, so first of all, let's get something defined here. What we have drawn there is a closed curve. All right? So instead of just having some curve that starts at a point and ends at a point, C, what we want is for the starting and ending point to be the same. All right? If we do that, then we have what's called a closed curve, or closed path. Path that has the same initial and terminal points. From that, we get this theorem. Or with that in mind, we have this theorem. The theorem says that if the line integral of a vector field over the curve C, right, f dot dr, which is work, right? That's work. If f is like a force field, then that's work. But that integral is what we call path independent, right? If and only if the answer is 0 for every closed curve path C in D. So here's the idea. You have some domain, all right, D. And you think about a closed path in this space. So I'm going to draw a closed path in here. Start, end at the same place. I could do a line integral over this. If I do the line integral over that and I get 0, right? Then does that mean that it's path independent? Not yet. This has to hold for every closed curve that I could possibly draw inside this space. So just because it holds for one curve inside of here does not mean it's path independent. It has to hold for every single closed curve that I could ever draw, and that's impossible for me to ever do, right? You understand that? Y'all with me? So that theorem, although it's nice, does not help me because I'm never going to be able to check every curve inside of some domain. But if we think about it, if that vector field F, if that vector field is conservative, right, then we know that the answer to that line integral is the two endpoints subtracted. And on a closed curve, the endpoints are the same. The starting and ending point are the same, right? So if I take these two and I subtract, if these are the same points, I should get 0, no matter what. And that leads us to this last thing. So line integrals on closed paths of conservative vector fields are path independent. Does that make sense to you? Crickets. Okay, you have a closed path. Starting and ending points are the same. It's conservative, which means you can use the fundamental theorem of line integrals, which means you subtract the two endpoints, which are the same. So when you subtract them, you get 0. What happens if you get 0 over every line integral? That means it's path independent. Okay, that's the idea. That only holds for conservative vector fields. Make sure I'm recording here. Whoa, did I kill this thing? Oh no. All right, so how do we determine, right? This is the big question. How do we determine if a vector field is conservative? Well, before we can do it, we need to distinguish some things because it doesn't always hold. We have to have what's called a simply connected region. So look at this right here. See this region enclosed by this curve? We call that simply connected. And one way to think about simply connected is this. If you draw any closed curve in here, imagine taking that curve and shrinking it down. Could you shrink it down to a single point? Think of it almost like a circle. If you just get a circle and you just start changing the radius, let the radius go to 0, won't it go down to 1 point? Yes? If I take any closed curve in here and I start shrinking it down, I can shrink it to 1 point. This is not a simply connected region because, of course, if I draw this, I can shrink that down to 1 point, right? But if I draw this one right here, if I try and shrink this down, this is a boundary. And I can't get the curve past that boundary, so I can't shrink it to 1 point. Got it? It's a hole. It's a little donut, kind of. So that's a simply connected region. This one is not. So here's the theorem. What do we need to be able to say that a vector field F is conservative, which is a very strong condition? Well, first of all, let's let the vector field have two components, all right? So right now we're looking at only vector fields that are two-dimensional. You'll have to wait for a few sections before we show you how you can do it for three-dimensional vector fields. But let's call that first function here p of xy, because it could have x's and y's in it. We'll call the second function q of xy. Let that be a vector field on a simply connected region D. So it has to be a simply connected region for this to work. Suppose that p and q have continuous first-order partial derivatives. That means I can take the partial of p with respect to x, I can take the partial of p with respect to y, I can take the partial of q with respect to x, I can take the partial of q with respect to y. So if all of that is true, then here's all we have to do to check. We just have to make sure that the partial of p with respect to y is equal to the partial of q with respect to x. Now, you might be asking yourself, why is that all we need to check? And that's a little bit beyond what I want to get into, all right? We could get into why that condition has to be met, but then you can start getting into some deep water, all right? So we will just take it on faith. Is that okay? All right. So that's a simple check, isn't it? You just can check some partial derivatives, see if they're equal. If they are, you're conservative. And if you're conservative, then you're path independent over any closed curve. So is this vector field conservative? This shouldn't take us but a few seconds. So I'm going to call this one right here P. Call this one right here Q. And I'm just going to do a quick check. Is the partial of Q with, I keep on doing it backwards. I did this in the homework also. I'm going to follow the notes. Here's what I'm checking. Is the partial of P with respect to Y equal to the partial of Q with respect to X? Yes or no? Well, what's the partial of P with respect to Y? 2X. What is the partial of Q with respect to X? 2X. These are the same? Check. It is conservative. But that means, right, that means that F is equal to the gradient of some scalar function. Guaranteed. What don't we know, though? What is that scalar function, right? What is the scalar function? Do you think it's useful to have what the scalar function is? Do we even need it? On a closed curve, you wouldn't. But on just a regular curve, if you wanted to do the line integral, you would need to know the value of little f at the two endpoints. So I actually need to know what little f is, don't I? In order for me to do this? Right? Integral. That's the fundamental theorem of line integrals, right? That's it right there. So if this is if capital F here, vector, is the gradient of f, which it is in this case, then I would just need the two endpoints of the curve, which would probably be easy for me to get, but I would also need to know the scalar function. So this test just allows us to say yes or no, it's conservative, but the next natural question is, how do we find little f, right?
So if it's not conservative, then I go.
If it's not conservative, then there's no need to go look for it. All right. So if you know that capital F is conservative, right? If you know it's conservative, then we want to find the little f that creates that vector field, right? And that little f is called the potential function. That's what we call it. And now we actually go through the process of how you find potential functions. And we use what's called partial integration. Not partial differentiation, but partial integration. So let's do it. So first question, is this a conservative vector field? This is a different example, isn't it? So call this one right here, call that P, call this one right here Q, and do your quick check, right? I'm going to check my partial P with respect to Y, and I'm going to compare that to partial Q with respect to X. What is my partial of P with respect to Y? 2X, that's it? This isn't the same one, is it? No, okay. And then the other one, partial of Q with respect to X, 2X. It's not always 2X, okay? So it is, it is a conservative vector field, right? So it has a potential function, and we need to be able to find it. So let's find it. So I'm going to write down what I know. I know that capital F is actually the gradient of little f, which I know by definition is this vector, right? Which for us in this particular problem is 1 plus 2x y plus natural log x comma x squared. Right? That's what I know right now. I'm going to start by writing down the first kind of solid piece of information that I have. And that is I know that whatever f is, right, that its partial with respect to x is that. Right? That's what I know. So I'm going to write that down. Everyone understand what we're looking for is little f? Right? Okay. So I'm going to write this down. I have that the partial of f with respect to x is 1 plus 2xy plus the natural log of x. That comes from taking the derivative of little f, right, with respect to x. What I'd like to do is go back to little f. So I'm going to integrate this. Do you agree with this? Little f should be equal to the antiderivative of the little f, the partial with little f with respect to x. Do you agree with that? But that's just the integral of this thing, 1 plus 2xy plus natural log x with respect to x. Maybe I should have put dx in here, sorry. Do y'all follow what I'm doing? Going backwards, integrating. The reason we're calling it partial integration is because we're integrating with respect to only one of the variables, right? We have two. So just think backwards now. What's the antiderivative of 1 with respect to x? Just be x. What's the antiderivative of 2xy with respect to x? X squared y, right? And just double check. If I take derivative of that with respect to x, I would get 2xy. What's the antiderivative of the natural log of x? Well, that's from Cal 2. I know in my Cal 2 class, we do it once and I give them the formula. I let them write it on their formula sheet. But if you tried to do that integration on your own like this, you could do integration by parts to get this. It turns out to be x ln x minus x. Okay, is that all right? Take that on faith? Yeah. This is the antiderivative of the natural log of x. But anytime we integrate, we always had this what at the end? Plus a constant. And this is where things are going to get a little tricky. All right? Because I cannot just put plus c. And the reason is because what if this over here, I'm just going to show you just for demonstration. What if this over here said plus y cubed? Would I know the difference? Like if I asked you to take this right now and differentiate it with respect to x, would you get this? Yes. Yes, because when you got to y cubed, you would say the derivative is what? Would be 0 with respect to x, right? So you don't know if this back here is a constant or possibly something with y's. Understand? It could be a constant or a function of y. So what we do is instead of saying we have a constant of integration, we actually have a function of integration. And here's what I can tell you about that function. If it has anything in it that's worthwhile, it's going to have y in it. Right? It may turn out that this doesn't have a y in it, but it could. Right? Understand this? Sure? Okay. Now, I did see some x's canceled here. Did anyone see that? So where I am right now is I'm saying that little f is equal to x squared y plus x ln x plus some function of y that I don't really know what it is, if it even is anything, right? So we're getting closer to knowing what little f is, but we still have this gray area right here that we're not quite sure of. Yeah? Okay, so now I'm going to move to the next part. I'm going to use the other piece of information that I'm aware of. The other valuable piece of information that I have is that this this piece right here is actually the derivative of f with respect to y, isn't it? So I'd like for us now to take what we know about f, which is this, and I'd like for you to take the derivative of it with respect to y. So what is the derivative of f with respect to y based off of what we have here? So what is it? X squared. Derivative of this with respect to y? 0, right? That's all x's in there. Those are all constants. What's the derivative of g with respect to y? G prime of y, right? I'm going to write it this way. That's okay. That means the same thing, right? We're taking derivative with respect to y. Understand? But I know that that has to be equal to what?
X squared.
X squared, right? But this must equal x squared. So I'm hoping that you're seeing that this piece right here came from what we've developed about f, and this piece right here comes from what we know we have to have. So we set them equal to each other. And if you look at this just as an equation, right, you can subtract x squared on both sides, and you would get what? The partial derivative, or the derivative of g with respect to y, must be 0. Now, can you tell me what g of y is? Because that was the only piece that we didn't know, right? Here was little f. That must be a constant. Right? G of y must be a constant, because the derivative of a constant is 0. Now, be careful here. Could g have an x in it? No. Because we said when we were going back here that the worst case scenario is that this has y's in it, right? Or a constant, but no x's. Because if it had x's in it, then that would have contributed to our derivative earlier. So I know for sure that doesn't have x's. So when I integrate this, the only thing it could possibly be would be a constant. So that means that g of y, not derivative, that's derivative, this is g of y, is equal to some constant. You can use c, anything you want. I think the book uses k, but I'm going to use c. So c is a constant. And that's it. You're there. Tell me what little f is. Little f is x squared y plus x ln x plus c. Now, if you want to, you could write, instead of little f, you could write f of xy if you didn't want to write little f like that. And the good news is that when you find a potential function, you can always check your answer, right? You just take the gradient